Yes, welcome back to the Diffy Q jungle. We're going to wrap things up today. We're going to tackle our last topic in this chapter, and it's a very special one. One of my favorites that we'll talk about all year, and that's the Logistic Diffy Q. Well, I guess the reason I like it so much and appreciate it so much is it's so useful and practical in the real world. I think by the time we're done with this lesson, you'll agree with me that we can look at a variety of facets of life, and whether it's the rate at which people enter a stadium or it's the rate at which a certain population increases, it's very, very practical in real life. But we'll get right to the bones of it. We have this particular proportional relationship here that we're going to try to dive into. We're going to read this statement here and try to translate it into a calculus or a mathematical equation. And it's a mouthful. We may have to reread it a couple of times to try to get our brains wrapped around it. But basically, it starts off, we're going to say that a population is changing at a rate. So right there, I'm going to say dp dt. Proportional, we've seen that word a number of times. That pretty much implies that we're gonna be using a k here. Is proportional to both the current population, which is p, and is a word that usually means multiply, the difference between the carrying capacity and the population. And carrying capacity is a totally brand new word that we haven't seen before. We're going to use the letter M for carrying capacity. Difference means we're subtracting, so I'm going to say M minus that population. So there's the Diffy Q that we're going to base everything off of today. The good news is there are, it looks like a lot of chaos and a lot of letters there. There are only two variables. P is a variable, T is a variable, K and M are both constants. And just as a important side note, it's going to be important later on, is that T is the independent variable. Okay, when we grew up doing math and through 8th, 9th, 10th, 11th grade, our independent variables were always X. But we're going to say T is our independent variable. And then that means P is my dependent variable, much like Y used to be. And the key that we're going to look at here on the next slide is exponential growth, the Diffy Q that we did not too while ago. Exponential growth is unlimited. However, but when describing a population, for instance, there often exists some upper limit past which growth cannot occur. And that's where we get real practical and realistic. One more question before we move on here is that Diffy Q that we just wrote, is it separable? That's been a popular thing lately. Is it separable? Could we possibly get all of our dependent variables on the left side and all of our independent variables on the right side? I think we definitely could. I could say dp divided by, I'm going to take this p and the quantity m minus p and divide both of them over. Notice I did not divide the k over with the p, and that's something we've seen a lot lately, where we're dividing that k over to the left side, and it's not an illegal move, but I think it's making our life a little more hectic by having a constant down there in the denominator. Anyway, we'll leave the k over here on this side, we'll multiply the dt over. And so we've just proven that it is a separable Diffy Q. I used to spend considerable time talking about how to solve this one. In the long run, I guess I haven't seen... it's not something we need to know for the exam, I guess. It's something that I think is beneficial. So what I'm going to do is I'm going to make an offer to you. I'm going to offer an additional 10 points on this week's spiral for anybody who takes the time to solve this Diffy Q and then solve for P. So we're looking for the solution to this Diffy Q. It'll be using an extra page at the end of your spiral, and I'll offer an additional 10 points to anybody who can walk their way through that. So a few lessons ago, we talked about an exponential Diffy Q model. And basically, we said that some variable y was growing or changing at a rate proportional to the current amount of that variable. And then we talked about separating the variables, and we said that we knew if we solved it, we'd get y equals c e to the kt. And the solution curve looked like this. And I want to emphasize the fact that that solution is exhibiting what we like to call unlimited growth. In other words, as t approaches infinity, so also is the y value approaching infinity, and that's what we describe with as unlimited growth. Contrary to that, today's logistic Diffy Q model, we said that the Diffy Q says that we could use y's, but I'm just going to stick with p's because it most usually describes population. Proportional to both the population and the difference between the carrying capacity and that population. Solving it is possible. We haven't done that yet. But what we're going to find out here in a little while is that solution curve it starts off exponential. But then what it does is it kind of takes a turn in the other direction and it curls this way. And there's some horizontal asymptote here at y equals m. And so what you'll notice is that there is not unlimited growth. There's a ceiling or a cap on what we're actually capable of. So we're going to say that as t approaches infinity, this time y doesn't approach infinity, it approaches some value known as m. So no more unlimited growth. That's the practical part of today's lesson. So we're going to dive in and try to describe these letters and all these variables a little more in depth. But we said that the rate at which the population is changing is proportional to both the current population and the difference between the carrying capacity and that population. So here we go, dp dt. That just describes the rate at which the population is changing. No big shocker there. The word rate's probably the most important word of our entire course. K's not super exciting. He just represents what we like to call our growth factor. It's a constant. It's usually a very ugly number. We several times we'll use our calculator and just store it. P represents the current population. And the letter M is the most exciting one today. I think it's the new component. That's called your carrying capacity, past which growth cannot occur. A lot of times, population biologists, for instance, they may be studying a herd of deer or something in a region of the state, and the forest that they live within can only sustain so much growth, and that's where we get that limiting factor. We're going to practice sketching our logistic solutions. Again, we have not solved this one algebraically. That's up to you this week if you have time and are interested in those extra 10 points. But we can certainly sketch the solution. We've used a computer to generate a slope field based off of that Diffy Q we wrote earlier. And what if they said, you know what? P of 0 is equal to 200. For instance, at the moment when t equals 0, P, or population, equals 200. Here's your t's, here's your p's, so we know that the population or the curve starts right there, and then we're going to sketch the solution curve. So you'll notice it's going to flow kind of through here. It's very exponential. It's behaving in a very exponential pattern so far, but then we're going to kind of curl the other way, and we approach this horizontal asymptote up here. They could flip this one around actually, and they might, once in a blue moon, they might say something like P of 0 equals 1200. There are some other real world phenomena where we may start above that M value up here, and it's not quite as exciting. You do curl down and then you become asymptotic to that horizontal asymptote. So just so you're aware that sometimes we do start above that line. The thing here, I want to pose two questions. I want to focus, let's go back, we're going to use the green color here. I want to focus on that first solution where we said P of 0 equals 200. Two things here. What is the limit as t approaches infinity for, we'll say, the function P of t, versus what is the limit as t approaches infinity for P prime of t? So first things first, now P of t represents the solution curve itself, the curve that we just drew up there, and you notice as t approaches infinity and gets really huge, the values of P approach m, which in this case was, if we scroll up a little bit, you'll see that the horizontal asymptote was at 1,000, our carrying capacity is 1,000, therefore the limit equals 1,000. But then the second question I posed, we're referring to P prime. P prime is measuring the slopes, and as t gets bigger and bigger, the slopes are getting closer and closer to 0. And that'll be true for all logistic Diffy Qs. The slopes will always approach 0, even if we're approaching from above or below. And then the last thing they might throw at you is they might ask you, what's the range of the solution curve itself? What's the range of P of t? In the range in this case, we would say it starts as low as 200 and it goes as high as 1,000, but never actually touches 1,000. Notice we're inclusive on the left side, but non-inclusive on the right side. We'll use that parenthesis. Pretty much the same practice here. What if they said P of 2 equals 1 and we wanted to draw a solution curve through that? Let's get rid of that y. Let's pretend that that says a P of t right there. So let's see, a t equals 2, p equals 1, so we're right around right there. We need to draw a curve. It's going to come up and then become asymptotic right there. Not the best curve I've ever drawn, but you kind of get the point. We can see that there's an asymptote right through here. That's our m value, or our carrying capacity. Vice versa, if they had said that maybe maybe they had said P of 0 equals 5, we'd have started up here, drawn a curve that descended very quickly, and then became asymptotic to the line y equals 3 or P equals 3. Well, here's a very interesting question. At what moment is the solution curve growing the fastest? And so most of our solution curves are going to behave in this fashion, where we start off exponentially and then we curl and become asymptotic to some line y equals m. Now, by definition, a point of inflection is the moment where we are maximized. Now think about this. This is a little in-depth, but usually when we talk about points of inflection, we're thinking second derivative, and that second derivative's got to change signs, right? Well, let's suppose that the second derivative changed from positive to negative. Not only have we proven that y, the original function, has a point of inflection, but we've also proven that y prime has a relative max at that point, because y double prime is just simply the first derivative of y prime, and therefore we know that at the moment when y double prime changes from positive to negative, y prime has a relative max. So basically we're saying, by definition, at a point of inflection, that's when the curve is either increasing or decreasing the fastest, which in this case we're increasing the fastest right there. Something very special about these logistic Diffy Qs. That point of inflection is guaranteed to occur at m divided by 2. That's a stone cold lock. That'll happen every time when we're describing a logistic solution. So our point of inflection is describing the point on the graph where it's increasing the fastest, and that's guaranteed to happen at m divided by 2. I want to emphasize, we've always described our points of inflection in terms of the independent variable, whether it be x's or t's. This is the one and only time throughout our entire course where we will describe our points of inflection in terms of y, or in this case p, known as the dependent variable. But it's just a very unique characteristic that we need to know. All right, now we're going to change course a little bit. We're going to do some rapid fire. I'm going to throw a bunch of Diffy Qs at you that I've created, and we're going to answer 2 questions about them. The first thing we're going to try to decide is this Diffy Q separable? And then if it is separable, we'll talk about whether it is a logistic model or not. Okay, and I'm going to try to throw a lot of different variables at you and keep you on your toes and test you a little bit. First things first, who's the independent variable here and who's the dependent variable? Well, looking at your rate of change right here, whoever's on the numerator, that's guaranteed to be your dependent variable, and whoever's in the denominator here, that's guaranteed to be your independent variable. So let's compare. Well, first of all, we've got to decide whether it's separable. I'm getting ahead of myself. I'm already trying to decide whether it's logistic or not. Is it separable? I think we'd agree that this is an easy one to decide in our heads. We could simply take the dx down here, multiply it to the other side, and bingo, we've separated all the variables. So now the question is it logistic? Well, our logistic model said dp dt is equal to k times p and then m minus p. Did you notice how this variable and this variable and this variable all match with each other, and they happen to be the dependent variable? The only time you're going to see the independent variable is down here. That's the only time. So up here, this bear is the independent variable, just like this one is. That makes it not a logistic. If this was a y and this was a y, then we would say it's logistic, but because that's not the case, we're saying it's not logistic. All right, we're going to keep scrolling here. Like I said, we're going to do some rapid fire. We're going to throw a bunch of these at you. Number 2, let's say that the derivative of r with respect to t is equal to 6 times r. Are you feeling good so far? You're probably thinking, yeah, it's logistic so far. And then the quantity 3 minus t. So first things first, is it separable? I think I could divide this r over to the other side. I could leave the 6 there. I could leave the quantity 3 minus t there, and then multiply the dt over. So yes, this rascal is separable. Okay, however, is it a logistic model? I was feeling good right here because we had both of these variables were the dependent variable, but then once they threw that t there, and t's the independent variable on this one, that screwed everything up, and this one is not logistic because of that guy right there. If we changed it to an r, it would be, but in this case, no such luck. All right, let's go get another one here. Number 3. What if we said dv dt, yes, that is supposed to be a t right there, equals 12 times v, and then the quantity 50 minus v. First things first, is this a separable Diffy Q? I could say dv divided by, I'm going to divide the v and the quantity 50 minus v over there. I'm going to leave the 12 where it is. I'll multiply the dt over. Yes, this one is separable. Next question, is it a logistic model? We've got the trifecta going here, the trifecta v, v, v. Those are all dependent variables. They're in the right spots. The only time you see your independent variables right here. So I'm going to say yes, not only is this one separable, but it's the first one we've seen that fits that logistic model. Okay, got 2 more for you. Number 4. Let's say dA dt equals a squared plus t squared. Well, we've got our hands full here. Boy, this is one of those ones that looks pretty innocent. Your gut might be telling you it's separable, but we could stay here all day. We could try to subtract that t squared over, maybe. Or maybe subtract the a squared over would be a more logical attempt. But then what happens is you've got to multiply each term by dt. So you'd get dA equals, minus a squared dt equals t squared dt. And unfortunately, this dt is lingering on the left side. I can't think of any way to completely separate the variables. So this one's not separable, and it's not even close to being logistic. What we have over here didn't fit our model whatsoever. All right, let's throw one more at you, see if we can get tricky at all. Let's say we've got 1 over y times dy dt equals 8 minus y. Is this separable? I think so. We could leave the 1 over y where it is. We could then divide the quantity 8 minus y over. Notice I took that whole quantity as one chunk, divided it over, and then we'll multiply the dt to the other side. So just like that, we did separate it. Next question is this a logistic model? Well, let's try something here. Let's go back to that original. Let's go ahead and multiply both sides by y. So we got dy dt equals, we've multiplied the y over, and then we got the quantity 8 minus y. And I would say, yeah, by golly, this is a logistic model. We've got what I call the trifecta. We've got 1, 2, 3 dependent variables. They're in the right spots. And here's a little extra bonus question. What's the carrying capacity of this logistic Diffy Q? All you got to do is look right here. Now, as long as this coefficient right here is a 1, and that's important, as long as that coefficient right here is a 1, then all you got to do is look right here, and you could say my carrying capacity is an 8. And if they asked you what's the limit as t approaches infinity for that solution curve, we know that that solution curve is never going to get higher than 8, then the limit is 8 itself. It'll always be the carrying capacity on that question. Not to be tricked here, what if they wanted the limit as t approaches infinity for y prime. In other words, what's happening to the slopes? The slopes are getting closer and closer to 0 because the curve itself is flatlining. Okay, one of the trickiest questions they might throw at you, it seems like it's so easy to describe or identify the carrying capacity. That's simply our m value. But they're going to try to make things a little sneaky on us. For instance, look at this Diffy Q here. dp dt equals 2 times p times the quantity 6 minus p over 100. And it's very tempting to say simply that m has to equal 6 because of this rascal here. However, this number here is not the carrying capacity unless this term is p only. So what we've got to do is we're going to try to factor out a 1 over 100. In other words, tell yourself that I'm going to factor out a GCF of 1 over 100. When you take out a GCF, you are dividing that term out. And in this particular case, if you're dividing by 1/100th, you are actually multiplying by 100 itself. So as I factor the 1/100th out, we get 2 times p over 100, because we pulled that out. This 6 becomes a 600 minus p. Now that this term became just a p, now we can say that m equals 600. That's our carrying capacity. Okay, the rate of growth of a certain deer population is given by the differential equation dp dt equals p divided by 50 times the quantity 1300 minus p. And this is a very friendly Diffy Q. The reason I like this one so much is as you look at that last p value right here at the end, that term is strictly p. There's no extra coefficient or baggage to go with it. So we're in great shape. Right now your k value or your growth factor is 1 over 50 and our carrying capacity is 1300. So simply here's two very typical questions. What is the maximum number of deer that the forest can sustain, whether it be because of food or whatever the case might be? We're going to simply say that m equals 1300. That's the maximum number of deer. If we did graph the solution curve p, it would look like this, where it is asymptotic to the line y equals 1300 or p equals 1300. The next question here, at what moment is the population growing the fastest? And that's where we talk about our points of inflection right there. Our point of inflection is guaranteed to occur at half of m divided by 2, which in this case is going to be at about 650. So just remember that 650 is the dependent variable's value. So we're going to say at the moment when p equals 650. That's not at the moment when t equals, but at the moment when p equals 650. Okay, here's our last problem for the night. And again, it's a mouthful. We may have to hit the pause button and reread it several times to get our brains fully wrapped around it. But again, a very practical problem that you could basically, whether you're talking about a rock concert or any kind of sporting event, the rate at which people enter that stadium typically follows a logistic model. And so we're talking about the rate of change of the number of people in the New Orleans Superdome as game time approaches is modeled by Logistic Diffy Q. The maximum number of people allowed in the stadium is 84,000 people. So right there, that's your maximum amount. I'm going to make a mental note to myself that m, or my carrying capacity, is 84,000 people. Now they came in and they said, well, at the moment, at the time of 12:30, about half hour before kickoff probably, the number of people in the stadium is 30,000. And is increasing at a rate of 50,000 people per hour. And that's one of the crazy things about people entering a stadium is that it's always usually a mad rush and there's a lot of chaos all at once. But we're going to try to write a differential equation, specifically a logistic Diffy Q, to model this situation. We're just going to summarize at the moment when t equals 12:30. Let's see here. We know that P represents the population. The number of people in the stadium is 30,000. And we also know at that same moment that the rate is equal to 50,000. So here's what you're going to find out. the fact that it occurs at 12:30 is not a big deal. But what is a big deal is that these two numbers go together and they occur at the same time. If they just said at 12:45 or at 1 o'clock, as long as this number is occurring and it's matched up with this number, it's going to be a good thing for us. Now, as far as writing our equation, let's see. My model starts off with the idea that dp dt is equal to k times p quantity m minus p. Let's see, what do we know? We know that m is locked in at 84,000. And we also know, I'm gonna go nice and slow. Let's say dp dt equals k times p times 84,000 minus p. Okay. Now what we're really missing is the k value. We need to somehow get our hands on k. What is the growth factor? So what we could do is let's substitute the 30,000 in for our two p values here, right there and there. And then we'll grab that 50,000 and we could substitute him in for dp dt. And lo and behold, we could then go ahead and solve for k. So we got ourselves some number crunching, to say the least, but nothing that we can't handle. 84,000 minus 30,000. I'm definitely running out of room there, but you get the idea. Okay, mathematically, I'm going to divide the 30,000 over right away, and we'll clean that up and call that 5/3. Equals k times, so do a little subtraction there, we got 54,000. And the last thing I'm going to do is divide that 54,000 over, and I'm going to get 5 over 162,000 as my k value. And the last thing I need to do is just finish it off and write my equation. So we could say dp dt is equal to 5 over 162,000. What a glorious number that is. Times p times a carrying capacity of 84,000 minus p. So I nailed my two constants. I found my m, I found my k value, and everything else is a variable. And there we go. There's a logistic model to represent or describe the rate at which people enter the New Orleans Superdome. So there's our first lesson of the week. Hopefully you had a good Thanksgiving. Hopefully you survived all your shopping injury-free. And hopefully you found some good gifts in the things you set out to find. So rest up, and we'll see you tomorrow.